So I don't have a ton to cover today. I'm going to finish section I started last time on Frobenius method. I have one more example to go through and one more things stuff about regular singular points. But first, quick announcement. I don't expect people didn't really take much advantage of this, but in case anyone wants to, just want to make clear that everyone has the option. So, what you can do any homework problems that are not assigned, but from sections that are assigned, up to multiple each. So, for example, if you see one that I've been assigned, but it looks easy, give it a shot. You know, at least one student who's interested in taking advantage of it, so of course, you know, get open to anyone. Again, don't expect people to take advantage, but it's there.
Does that mean if there's a homework problem maybe I don't want to do that's assigned, but there's one that I find is easier and I do know how to do, I can just do that one instead?
To a point. The reason why I say that is because assigned problems are generally going to be worth more than 10 points each. So you can reduce your losses by doing that wrong. I guess if it's a really big problem, then we can talk about it.
Well, it wasn't that I was going to, it's just more I was curious, like, that's the case, then this why.
Well, I will say that when I'm choosing homework problems, I'm not talking going for the hardest ones. So, not necessarily the easiest ones either. But I look at ones that focus on problems that are interesting. Now, my definition is probably different from yours. But, okay. Now, so for Frobenius' method, we have a second order linear homogeneous ODE with constant or variable coefficients. Coefficients are functions of x. And just a quick recap from last time, we assume the series, the solution has this form as a series. Well, it may not fit the usual definition of power series because the value s here, which has to be determined, is not necessarily an integer. And then we figure out, after substituting this into the ODE, what must these coefficients a, j be. So now we're going to do that with a ODE called Bessel's equation, which leads to some very important functions called Bessel functions. And we'll learn all about Bessel functions later on in the semester. But now we're going to see how to get them as a series. Because there is a kind of ODE that techniques you learned in your first ODE course wouldn't help you with because the coefficients are functions of x. So, first thing I do, take this power series, take its first and second derivatives. In this case, it's using power rule, and substituting those into the ODE. And doing that and no other algebra as yet leads me to this. What do we have? We have x squared, and then this is the second derivative. Just taking second derivative term by term. Plus x times first derivative, get the power rule term by term. And then I have plus x squared minus x squared times just the power series itself. But I need to get this into a form where I can try to solve for the coefficients. And that means what we want to have is one summation, as much as possible, one summation, where all the coefficients in that summation must be 0, because the right-hand side is 0. So, I'll take the x squared and distribute it through the second derivative. That's just going to change this exponent here. Same thing for the first derivative term. Just take the x and distribute it from there. It is nice, then we have x to the f plus j in both summations. And we have that, and then I take the x squared minus n squared, break that up. And in the first sum, I'll distribute the x squared through. So now we have x to the s plus j plus 2 here. So now we have x to the s plus j in most of the summations. So now, and all summations start at j equals 0. So I'm going to group this into 1. But this is still not in the form I need yet that will help me solve for the AJ. There's still a little more work to do. Because I want to have just one power of x in a summation. So what I'm going to do. Oh, someone have a question?
I think it was just your echo.
Oh. Yeah. Right. Okay. So because I have x to the f plus j here next to s plus j plus 2 here, what powers of x am I going to get if I start with j equals 0, 1, 2, and so on? Well, here I'm going to have x to be s plus 1, s plus 2, and then here I'm going to have s plus 2, s plus 3, s plus 4. So whatever powers of x these have in common, I want to have a summation that includes all of those. So now we're starting from s plus 2. So any lower powers of x than s plus 2, I'm going to write separately. So, and this is in keeping with what I showed you in the previous example. Because it's a second order ODE, you should write the terms corresponding to the two lowest powers of x separately. So, then we this term of x to the s, and this term of x to the s plus 1 corresponding to j equals 0 and j equals 1 from here. And then everything else, so the rest of this part, starting from j equals 2 on up, I've written here, and then this, I've just kept as is. Now the reason why I'm doing that is so that I can combine these into one summation by index shifting. So if I take this summation here, and I decrease the starting index by 2, then I'm starting at j equals 0, which lets me combine with this sum. And then, by decreasing the starting index by 2, I will increase j by 2 throughout here. So wherever I see j, I'm going to replace it with j plus 2. So aj becomes aj plus 2. S plus j becomes s plus j plus 2. And then this power of x becomes s plus j plus 2, which agrees with the power of x we have here, thus letting me to combine them. Okay, something seems off here. That should be s plus j plus 2 based on what I had before. Well, I'm doing some checking off screen. All right. Are any questions about how I got to this point? So in general, the goal is to have a summation involving a single power of x times something. In order to get that, the terms corresponding to the lowest two powers of x must be written separately. And now because all of these terms involve, here we do have a power series again. It's just that these coefficients of x to the s and x to the s plus 1 are not in exactly the same form as this. That's no reason why they have to be written separately. But this is a power series. If a power series is equal to 0, all the coefficients must be 0. So that's how we're going to find the a's, setting this coefficient equal to 0, this one, and then all of these. And the term corresponding to A0, we set that equal to 0, and that gives us the indicial equation. A0 itself cannot be 0. The rest of it has to be 0. So S is equal to plus or minus n. And I should have made this clear at the outset. We're going to assume that n is an integer. It's allowed to be positive or negative. So now our lowest power of x has been established. That's going to be either plus or minus n. Now let's look at what happens if s equal 1, or the term involving a1. It should be a1. So if I go to this term right here, a1, and I set s equal to n or minus n, and then simplify as much as I can. This is what I get in the case of s equal plus n, and this is what I get with minus n. But the only way that these can be 0 is either a1 is 0, or n is equal to plus or minus n. But we're working on the assumption that n is an integer, so that's not going to happen. So a1 is going to be 0. Now, we go to the remaining terms. This expression in the curly braces has to be 0. So we go ahead and set that equal to 0. And we're going to solve for aj plus 2 in terms of aj. Whatever coefficient is the highest index, you solve for that, because the idea is coefficients are determined by earlier coefficients, lower number coefficients. And that leads to this recurrence relation. So each coefficient depends on the one, 2 prior. I'm not going to focus in the case of s equal to plus n. I'll go minus n later. So if I go ahead and set s equal to n, and I expand this, so n plus j plus 2, I'm going to get some cancellation. I'll have some n squared terms to cancel. And this is what's left. So a2 comes from a0, a4 comes from a2, a6 comes from a4, and so on. a3 comes from a1, but a1 is 0, so a3 will be 0. And a5 and so on. So all unnumbered coefficients will be 0. So we're only going to have the even numbered ones. We just need to figure out what the pattern is from this recurrence. And the best way to do that is to work a few out and see what pattern emerges. So go ahead and compute A2, A4, A6. So what do we see when we do that? First, there's this minus sign. There's a negation that happens every time. So we're going to have alternating signs. You're always going to have A0 as a factor. And we're multiplying these increasing numbers. We have n plus 1 in A2. Then in A4 we have n plus 1 plus 2. And then in A6 we have n plus 1 plus 2 plus 3. That means there's going to be a factorial involved. But what factorial exactly, we still need to figure that out. And then the numbers that we get here, A4, 32, 384, you might not really be able to figure it out just from those, but it's helpful to see what's happening from one coefficient to the next. So, because the idea is 32 would be 4 times 8. 384 is 4 times 8 times 12. So what you're doing is you are multiplying multiples of 4 in the denominator. So those patterns you can use to figure out a general formula. That's what I'm showing you here. So we have minus 1 to the p. So we're 8 to 2p. So here p equals 1, p equals 2, p equals 3. And I'm working with p because that lets me to describe, first of all, a sign pattern is minus 1 to the p, but alternating. And then look at the numbers multiplying here, n plus 1, n plus 2, all the way up to n plus p, where p equals 1, 2, 3. And then the multiples of 4 that are being multiplied together, so we have this example right here, 4 times 1, 4 times 2, times 4 times 3. Whatever p is, it goes all the way to 4 times p. So this is what could be gathered from these examples here. And I guess if you really wanted to, you could carry out a proof by induction to see that it really is true in general, but we're not going to do that. Any questions about how it got to this point? So now I want to be able to write these as a concise formula so that all coefficients can be described. And having these kind of expressions where like the dot, 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 that gets a bit cumbersome. I like to have something more compact than that. So could anyone tell me what would be a way to describe this, considering that we have numbers 1 to 2 up to p in here? So what's the concise way to express that? There's a factorial. What factorial? Yes, p factorial. So that accounts for the 1 times 2 up to p. And then what else would you have of this?
4 times p.
No. There's something else before. Because look at because what you just said, if I heard you correctly, said 4 times p factorial. That would mean there's only one 4, but there's a 4 in each of these products.
Did it make the product summation thing?
You wouldn't really need that for this. So consider how many factors of 4 must there be in this. How would you express that? warmer, not 4p, but because,
The next one?
yes, well, typically, is that what,
No, it was just funny. Explain, yeah.
okay. Yes, 4 to the p. Okay, oh, we got there. Yeah, so 4 to the p times p factorial. Okay, so that takes care of this part. Now here, we have consecutive numbers being multiplied, which suggests factorial of some kind. But, so it will be using factorial, but we have to account for the fact that the product starts at n plus 1. So what would that mean? So how do we describe this by factorial?
N plus p factorial over n factorial.
Yes. So you take all the numbers from 1 to n plus p, multiply them, and because 1 through n are being excluded, you divide by n factorial. So factorial of the highest number being excluded, and there you go. So okay, so this part only counts for factorial, that part. And p factorial down below for this, and then that is divided by n factorial, so n factorial here is the numerator. And now we have that. So now we have this in what's called closed form. So not involving any like summations or products of a increasing number of terms. I think once I'm change that appears superfluous now, but it actually will become useful later. I'm going to change the 4 to the p as rewrite it, change it to 2 to the 2p because 2 squared is 4, so you can. Because I'm gonna need that 2 later on. Any questions about how we got here? So that's our solution. So because that's a to 2p. So here we have normally our power series is a j x to the s plus j. S is equal to n. Because we only have even powers involved, even number coefficients, we're going to have 2j instead of j. So here I just replace p with j throughout. A0 is a common factor, so that gets pulled out. Now A0, I'm free to choose it however I like, as long as it's non-zero. So, I'm going to choose something that's convenient. I have this n factorial that I can cancel. So I think it's set to, whoops. Need to put that in parentheses. So 1 over 2 the n factorial. So the n factorial down below will cancel the n factorial up top. And then, because by introducing the 2 to the n, now I'm going to have 2 to the 2n plus to the 2 to the n plus 2j. This is why I rewrote 4 to the j as 2 to the 2j, because I have x to the n plus 2j here. So by this choice of A0, I'm going to have x to the n plus 2j up top, 2 to the n plus 2j down below. So I incorporate those into one fraction. So that's the only reason I went from this to this. And that's called the Bessel function of order n. So this is a solution for each n. It is a solution to Bessel's equation. Any questions about the finalizing of that? Yeah.
For physical purposes of like ways, the nodes of the function.
Okay. So I'm not to my Bessel function knowledge, but well, actually,
And you don't have to answer it now, it's just we're touching on it and we're like,
actually, yeah, chapter I think 15, I believe, gets into Bessel functions. Okay, and while n is not required to be an integer, that's the case we're considering here. And remember something about the behavior of Bessel function of order n. Especially when x, especially when x gets large. Oh, it's a shift. Okay. Right. I'm going to take a moment to show this. Okay. So for instance, for what's Bessel functions? Here are Bessel functions of the first kind, and okay, yeah, and so you see, like they get damped over time. The first one starts out at 1, then all others start at 0 when x is equal to 0. And notice that they seem to have these shifts of one another. And in fact, if I go to a section here called Asymptotic Form, so this gives approximations of the Bessel functions when x is small or x is large. So for instance, when it's small, so it's a multiple of, so it's like as a polynomial form of a higher degree. So it's like a multiple of z to the n for whatever n is, which therefore makes sense that when z is equal to 0, j0 will be 1, all others will be 0. And then for large arguments, sure enough, it behaves like a cosine. And the role of your index, the alpha here, n in the notes, is a shift. But also we have this out here where that's going to 0 as z goes to infinity. But it's going to 0 slowly, because z to the minus 1/2 goes to 0 slowly. So that leads to what you see here, that yeah, there's some damping, but not a whole lot. And the fact that the index leads to a shift shows that why we have these cosine-like waves in lockstep. Okay. Any more questions up to this point? One of our research projects several years ago dealt with Bessel functions because if you have the Laplacian, so uxx plus uyy in 2 dimensions, we're going to talk later in this class about eigenvalues and eigenfunctions of linear differential operators such as the Laplacian. And for most parts, stick with just one spatial variable, so your domain is just an interval. But in 2 dimensions, you could be solving an equation like the Laplace equation, a PDE, on a domain of whatever shape. And so my project was trying to figure out eigenfunctions of an eigenvalue of the Laplacian operator on an arbitrary shape, especially very complicated shapes. Like for instance, we consider like a domain shaped like an L. When you have no domain, no boundary conditions whatsoever, you can express such eigenfunctions in terms of Bessel functions. That's really what I was doing, trying to find a linear combination of Bessel functions that would satisfy the boundary conditions I want. And all this work about that, there's been a lot of work done on solving Laplace's equation on a general domain. And it grew out of this paper written a long time ago, where the title of the paper was, and I'm paraphrasing here, but can you hear the density of a drum? And mathematically, what that question was about was, is it possible to, if you knew the eigenvalues of a Laplacian that came from some shape, but you didn't know the shape, do those eigenvalues uniquely define the shape? Unfortunately, the answer is no. It's possible to have two very different shapes for which the Laplacian has the same eigenvalue. So we're going to learn more about eigenvalues in the next chapter, but there's just an interesting work to look into. The double Bessel functions. That project, I got kind of sick of them actually, but okay. All right. Now, because we have integer powers of x, and this part is always going to be even. So whether this power is even or odd depends solely on whether n is even or odd. Meaning, if n is even, the Bessel function will be a sum of only even power, a linear combination of only even powers of x. And then if n is odd, only odd powers of x. So the Bessel function of order n is an even function if n is even, odd function if n is odd. And this goes to what I was mentioning in a previous class about whether the differential operator that you have is okay. Well, in terms of n, okay. Actually, I'm going to say Bessel's equation has symmetry. Ah, okay. Like, if you replace x with minus x, but you have to be careful how you do it, because, okay, for instance, if I replace x minus x here, of course the x squared doesn't change. This doesn't change either. The x will be flipped. However, replacing x with minus x also has to do with differentiation involved. Because what happens if we differentiate with respect to minus x? Well, that's the opposite sign of when you differentiate with respect to plus x. So here we're going to have negate, so you're back where you started. Here, there's going to be a negation for differentiating with respect to minus x, but we also have a negation here that cancel. So, so in that case, we end up having symmetry with respect to x. So that explains why we have solutions that have symmetry. Now suppose but all this time I've been considering the case of f equal to n, where n is assumed non-negative. Now, if n is not an integer, we can replace s with minus n. We can go through this whole process again, which I won't do. And that's j from minus n of x. But if n is an integer, and we consider a case of minus n, Frobenius' method will fail. And a second order ODE is going to have two literally independent solutions. It doesn't necessarily mean that Frobenius' method is going to help you find both of them. What goes wrong in the case of s equal minus n, that can be seen here. Because suppose I replace n here with minus n, then when j is equal to 2n minus 2, this becomes 0. So we divide it by 0 and Frobenius' method breaks down. So that means that if we're going to find a second linearly independent solution of Bessel's equation in the case where n is an integer, we have to do something else. And we will in the next section. That's reduction of order. So we know what two solutions are there. It's just a matter of what does it take to get them. So more about that. When can we use Frobenius' method? We know it's going to work. Because we've just seen an example of where it will fail. So it depends on how your coefficients in your ODE, p of x and q of x, behave. What if they're not defined at a certain point? So there are three kinds of points that we can have. So if p and q are both defined, finite, point x naught, that's the ordinary point. Now, if either one of them are undefined, then it's a singular point. But there are two types of singular points, regular and essential. And the distinction matters. So if I want to go to infinity at a certain point, x naught, but this expression is finite, or if this expression, or both of these are finite, but that's called a regular singular point. So for example, if x naught is 0 and p of x is 1 over x, then x times p of x is 1. So it's not too strong of an asymptote, basically, is what we're saying. But if either one of these are still infinite, so in other words, multiplying by x minus x naught for p, or x minus x naught squared for q, if doing that does not cancel out the singularity, then x naught is called an irregular or essential singular point. Those are the ones that are a problem. We don't like those. Fortunately, we don't have that in Bessel's equation. So here, if I write Bessel's equation this way, divide both sides by x squared. Because remember, the ODE has to be of this form. Y double prime has to be by itself. If your equation is not written that way, you got to divide by the coefficient of y double prime. Then you have your p and q in the right form for purpose of determining if there are any singular points. So here, p of x is 1 over x, and then q of x is this expression here in parentheses. So they're both undefined at x equals 0. We have vertical asymptote there. So then we multiply p by x, and then q by x squared. And we get something in both cases that is defined everywhere. So we're good. This is a regular singular point. The previous example from last class, the simple harmonic oscillator, linear oscillator, those coefficients are defined everywhere. So at any point, x naught is an ordinary point. So those are ones that are not troublesome. So this theorem, I'll tell you Um, so, so if you have a point that is not an essential singularity, so it can be an ordinary point or it can be a regular singular point, then at least one of the solutions can be found, guaranteed, using Frobenius' method. How to get the other solution, that depends. You might still be able to use Frobenius' method, like in the case of a linear oscillator, or you might have to use reduction of order, like we will do next time with Bessel's equation. But one thing to keep in mind is, suppose you have a singularity at x naught, then oh, um, oh wait, okay. If x naught is the center of your series, but if there's a singularity at a different point, so a point that's the same distance from x naught as the singularity is, the series might diverge at that point. So be careful when you do have a like a regular singular point. That's why it's important when you find a series solution using Frobenius method, you should check it for convergence. Once it's radius of convergence, where might it diverge? So you might have points of divergence to be concerned about. All right. Okay. I was checking on something here, but I'm not going to find it. At least not yet. Okay. All right. We have a good amount of time left. Do you have more questions? Okay.
In scalar product, if you move it from the left to the right to the left, does it? Move it from the right to the left, does it always go like on the outer left
Right.
in order?
Okay.
If you're doing scalar product and you move it from the right to the left in order of how it's put, do you always put it on like the outer left?
Oh, I see. Okay. So in other words, like, okay, I assume what you're referring to is like a scalar product of functions, and you're taking like factors of those functions.
Specifically number 2 with the operators.
Okay. Okay. Yeah. Operators and functions, different answer. Okay.
Operators.
Okay. Yeah, you do need to put it to be left. Okay. So this is dealing with
Number 5.3, number 2.
okay. All right. Okay. So I'll start thinking here. More questions. All right. So you're referring to this situation where you have something like this for some operator. Okay. So Yeah, so you wanna move the A from the right to the left. And
And
that's,
if you already have an operator, a different operator in front of F,
right, okay, so we're going to answer this. Oh, I forgot the F. Okay, is that this applies. Okay, so in other words, you think of, because either F or G might be some more complicated expression. It must be undisturbed when you're doing this. So if you have multiple operators involved, like you do in this problem, then you want to move one operator at a time. So I don't know if that.
okay. Kind of.
So
There's an operator B in front of F,
okay,
right there.
okay, right. So so if I let F equal to say B times H.
Okay.
Okay, so this is where I go back to my comment about whatever F and G are, do not disturb that. Okay, or anyone else?
Or, but anyway, I have more.
Okay. Let's see. I keep going.
Okay. On number 3, when you're doing the partial derivative in terms of something and that's an operator, then are you always applying the partial derivative to whatever it's being like multiplied to, like applied to?
Right, and I think this is not the first question I got about this. So, okay, so for example, I'm taking this operator right here, and you're applying that to some function. Okay, so then you're going to apply, for example, this partial derivative with respect to that function. Apply that to the function first. Then result is multiplied by, in this case, x1.
Okay, because on the first operator, whenever it's partial derivative of xi, and there's an xi right next to it, then it makes sense. That kind of seems pointless of it being like that. But if it's directly or has like that partial derivative has to be applied to whatever the operator is being applied to.
Yeah, so, oh, okay, so in other words, looking at just this by itself didn't
Yeah.
seem to make sense.
No.
But, yeah, there's gonna be some function that can be acted on by first this, then that.
You just-
That's pretty good.
And then on number 4, if you're doing the scalar product and like i's are on one side and then j's are on the other side, or maybe this is I came across this one before, but you have I on one side like pi and then pj on the other side.
Yeah.
So you have to like at some point convert maybe like the j's into terms of i's.
Oh, okay, alright. So. So what you're referring to Okay. Um. Okay, so, and that's going to be, um, using this funny A to refer to the matrix as opposed to the operator like just like the textbook does. Okay, so I'm gonna talk about something here and then see if this is what your question's about. So you go ahead and you just work out what APJ is, and I'm gonna call that like polynomial Q of X. Okay. So what you're saying is you have each polynomial Pj expressed in like normal polynomial form, which we also call power form, but anyway. And then you carry out the operator A on it. So what you get here is just it's really expressed in monomial basis. And what you're asking is, are you supposed to convert that into a linear combination of Legendre polynomials? Is that what you're asking? I'm gonna type out what I'm saying. So if what you got from carrying this out is something of this form, okay, then so do you need to write Q Qx in this form? Of some other coefficients. Is that what you're asking? Like to change it from this form to this form?
Broadly, because since the PI and the PJ are different,
Right.
then at some point, don't you have to technically make them both in I's or both in J's?
Okay.
Just because it's implied in the very beginning, whenever it's in saying.
Okay. I feel like I have what you were asking, but I don't feel like I lost it. Sorry. So
This might be a thing where I need to work the problem more. And
Well-
then-
okay. Please try one more time. You can try your best. If you know.
So in the very beginning, in its like big form, just PI and then scale part with PJ. Then since it's in terms of I on the first one and in terms of J on the second one,
Yeah.
wouldn't it imply at some point you'd have to match them?
Okay, so it's the max part that I'm confused about.
Because normally whenever they're in different terms, then you have to do something where it's not I's and J's, it's either I's or J's. Either one or the other.
Because, and also the expression we get will depend on both. Because you're filling the entries of a matrix. And as for what the problem is asking about, okay,
But once you get your APJ, then that's just what you have, and then you have the scalar product of it.
Yeah.
Or, and then you do the scalar product with PI.
right, and yes. And okay. Now, so apparently this is not relevant to your question. Okay, yeah, and.
So that's another question about how it's relevant.
In case anyone was wondering, it's like, it's not.
Yeah, cause I didn't have to do that for like, 1.3.4, like I didn't do the summation or anything.
Yeah,
Okay.
yeah, and because the P's are orthonormal, you can just go ahead and take this scalar product, and that tells you what these are. Then these coefficients will fall out. If you went to the trouble of doing this some other way, then finishing this off would be trivial. But you might as well just take the scalar product. Okay, so as far as what the problem is asking, okay. So as far as what you actually need to do, and we'll see if that jives with what you're concerned about. Okay, so you already have the Legendre polynomials in whatever form. Okay, you go ahead and plug the operator, take scalar product of that with pi, just grinding out the integral. And yeah, you will have to do that for all combinations of I and j. And unfortunately, that's a 4x4 matrix. We have 3, 3, although the operator in question is okay, take a derivative and multiply by x. Some entries will be 0, so that'll help. Or might have a fairly simple form. Now, actually, I will mention a shortcut here. Oops. Oh, okay. Shortcut. Moves to a new page, it's annoying. Okay. If you use the fact that each pi is orthogonal to all polynomials of lesser degree, and because you take a derivative of a polynomial, that's a polynomial, multiply it by x, it's still a polynomial. And APJ is a polynomial. So if APJ is of lower degree than pi, then the scalar product will have to be 0. So that makes a lot of entries 0 right off the bat. I'll leave it to you to figure out, like, okay, if PJ is of degree j, what is the degree of APJ? Okay, I was in the middle of explaining what had been done in the problem. I didn't finish that. Okay, okay. Well, I got through just forming the matrix. So good on that part, at least. Okay. And that's all of part A. Part B, so you're going to take a scalar product of x cubed with each Legendre polynomial to get a vector of coefficients. So you're expressing x cubed as a linear combination of p0, p1, p2, p3, just by computing the inner products. And okay. So then what you can do, that's part B. Part C, if you compute ax cubed directly, then figure out its coefficients in electronic basis, again, by taking scalar products, although what you did in part B will help considerably with part C. So you have a vector of coefficients for x cubed, the vector of coefficients for ax cubed by scalar product of total polymers. And you want to confirm that if you take this vector of coefficients and multiply by the matrix A, you'll get this vector of coefficients. So it confirms that the operators of matrix works. So hopefully that.
That's
Okay.
always in practice. Something happens.
Okay, well, I'm on call. Okay, so a little bit of time left. Any other questions? Oh, okay. Oh, wait, which one?
5.1.
Okay. Okay.
On number 2, if in the steps I prove that it's only how do you say that?
Hermitian.
Hermitian?
Yes.
If I prove it's Hermitian only if A and B commute, then and it's proved that like you can't do that without that, then do you have to prove that the commuting also is equal?
Okay, so we gotta make sure both directions are covered. Okay, so I guess what you did was you went ahead and computed the like the adjoint of the product. Okay. So well, actually, even when you get for racks, will pull up naturally that what directions will go all at once. But because another way to think about it is, okay, if AB equals BA doesn't work, okay. If AB is not equal to BA, does it not work? Okay, then you're good. And that's probably the easiest way to look at it.
So as in AB equals BA, if that doesn't work?
Yeah, so if AB not equal to BA causes it to fail, then that's the other half of the proof.
Okay, so we'll have to prove.
Yeah.
Number number 3.
Yeah.
Is it assumed that A and B are?
I believe that is the case. Both dealing with the definition of quantum mechanical operators.
Or that's why I
And I remember that was defined somewhere in here. And of course, that's why I'm not.
I remember it being mentioned in the notes.
What?
I remember it being mentioned a couple times in the notes.
Yeah. Yeah. So it's working definition here, but yes. So the A and B themselves are Hermitian.
Yeah, one more. I'm done.
Okay.
Little star complex.
Yeah.
Would that mean something in doing the work? You use it in doing the derivative of the first one being.
Oh, okay. Sorry, context?
Oh,
Oh, okay. All right. Okay, so you're working with this expression and, well, and this expression doesn't turn out to be real anyway, but, okay. What you need to use for this, I'm not sure if you were using this already, is the fact that the scalar product of any function with itself has to be non-negative. So the goal is to write the given expression as something of that form, using the fact that L is reached.
I didn't ask the right question, but you answered it. I didn't ask the right question, but you,
Okay.
whatever I was questioning, you did answer it.
Okay.
So the scalar product of itself means it can't be negative, it's not negative.
Right. We're not sure to do your question, next focus on all that and more.
Norm,
Yeah, whatever works.